hot dog.
All right. Okay, so first, here's my example. I'd like to write this one down. This is going to be the example we're going to use basically the entire class. Hopefully it'll make sense once we get through it. So let's go x to the third minus, let's go with like 4x squared plus, let's go 5x minus 11. All right. This is my polynomial. I want to graph this thing, do all the little things correctly so that we can get what we call a very accurate graph for a polynomial. All right. So, the steps. These are all the rules and guidelines that we follow. These rules are not easy, especially the X-Intercept one we talked about on Friday. It's one of the hardest rules to go through, especially in factoring. I tried to pick a more complicated problem than what we did on Friday, because we need to get better and better. Now, some of you are gone. You need to get these written down. You have to have this stuff figured out. This stuff doesn't go away. I expect it for most of it, for the majority of the sections we have after this, that you can still remainly do this over and over and over. Because we're going to be looking at polynomials a lot, and you have to kind of estimate what certain answers are. That requires that you have to graph them. Okay, so first line, when we do this, marker's dead.
Red marker.
So first line, we have to look at the leading coefficient test. Now we talked about this on Friday. This test goes with the second rule, like they go hand in hand. This test where you look at the front number, the leading coefficient, on the biggest, highest degree. So this is the one I'm looking at. So this is a 1x cubed. Sorry, 1x cubed. I'm looking at the number out front. That number tells me a lot. If this number is positive, which in our case it is, then I know this won't seem like it makes a lot of sense unless you've seen a bunch of these. But positive number out front means this will be a normal graph, or a typical graph, however you want to say it. What I mean by that is it won't be inverted. It won't be a reflection, so where it's upside down. After a while, you get used to what these graphs should look like. I'll try to show you the hints as we go through this week. That how do you know what this graph looks like generically? How do you know what this graph? And we'll kind of look at those. Okay. If this number was negative, and this is what I was kind of warning you of. So if it is a negative number, then it is reflection of the graph across the x-axis. Now, I will show you what this picture is supposed to look like right now, once we get through the second rule, and then we'll talk about what happens if it was a negative number out front. What would that make this graph look like? Because the second rule really goes with this one. They go hand in hand. Okay, the second rule, number 2. End behavior. Okay, on end behavior, you're looking at where the tails are going on the outside of my graph. So, what you look at is the highest degree term, like this is the highest degree item. Now we're looking at the power of it. If the power is even, the tails go the same direction. So what I mean by that is when we're graphing it, the tails would both go either up or they both go down. If it's an odd number, do you agree that my power is odd, the highest degree? Then my tails go opposite directions. Tails go opposite directions. Now, this is where you get a sense for how these work. Even powers, like powers of 2, like x squared, if that was your highest degree, the tails go up. X to the 4th, the tails go up. X to the 6th, they go up. It's every even number, the tails will go up. If it's odd, one of the tails goes up on this side, and one of the tails goes down on this side. Does that make sense?
Yep.
Okay. So mine is an odd power, it's a power of 3. So one of the tails goes up to the right, one of the tails goes down to the left. And so what's going to happen here is I don't know what's going on in the middle. There's some weird stuff going down in there. We'll figure that out once we go through the next checklist, like the next few steps to figure out what the middle's doing. But I already know that outside tails going that direction. What I warned you of earlier, if there was a negative number out front, like let's say this was -1 instead. Well, now the tails are inverted, it would look like this. And the middle would do that thing again, whatever it's doing.
Wait,
Okay.
so what do you do if both the leading coefficient and the integer last number is negative?
This number, like this number's negative and that number's negative?
Oh, we haven't even gotten to that.
We haven't even got to that one.
Sorry, that's just where it hits
Okay.
this thing.
Yep. Alright, so tail's going that way, my other tail's going this way. Alright, do we understand my graph?
Yep.
Okay, again, you're just drawing generic pictures here. But they're going to be somewhat predictable in the nature of them, as long as you go through my checklist. Okay, so we have an end behavior, we have the leading coefficients. We're done, we're moving on to the next one. Step 3, this is the longest one out of all the steps. We have to do X-Intercepts. This will go with the next rule that comes up later. It's called Multiplicity Test. But X-Intercepts, you have to be able to do either 4 different rules for this one. And this one that I said, like, it could take the longest. Okay, the rules, if you can't figure out the X-Intercepts, number 1 rule. So these have secondary rules on the inside. Number 1, you have to set up a table and try to figure out where the X's cross. What do I mean by that? You plug in a bunch of numbers on the X side, like that. You can even put decimals. You plug them into that thing and read off what the answers are. Let's say this was a 7, this was a -5. Let's say it was like that. Well, then the idea is that you know that between these two numbers, it had to hit the x-axis. Because at 0, 7, 0, 7, 1, 2, 3, 4, 5, 6, 7. Again, this is an example. This is not part of your problem. I'm just showing you what would happen. And at 1, -5, somehow that graph hit the x-axis somewhere in between them. You could do it that way, where you can guess numbers. Okay, where you know they're kind of in the middle. That's called the intermediate value theorem. But there's always a number in between other numbers. Okay, that one would take a long time. You have to plug in numbers and do a table. I would not want to do that. I'm going to try to give you numbers so you can actually do these other rules. Rule number 2. The rule that I'm going to use on this problem. I'm going to factor. I want to factor that thing apart. Now, that requires that you know all 5 types of factoring. So in this one, it's going to require that I do grouping. It's going to require that I know common factors. It's going to require that I know difference of squares, all that good stuff. All right, questions at all about this so far? I'll do mine here in a minute.
Wait, so you're going to have to do all the rules for the X-Intercept?
For the X-Intercept, you have to pick one that you know you can accomplish.
Oh.
So like if I can factor, I don't need to do the table. If you can't factor, maybe this problem's like a square term, you can do the quadratic formula. Quadratic formula is that -b plus or minus square root thing, like if it was a square root thing. If it was a quadratic. Okay, 4th type. And this one we haven't learned yet. This is my goal by the end of this week, that you know this rule. It's finding the rational roots. It's called the rational root theorem. This is the one that I've been hinting at, that some of you said you've seen before. It's when you guess numbers that you think are X-intercepts. I'll show you the rules for how do you know which numbers to guess. And you literally long divide them out. You either use long division with the house, and long divide like polynomials, or you synthetic divide them. That's where you use that little box and you draw a line and put numbers across the top. I think Mr. Godden must have done it with you guys last year, because I've heard a lot of people saying that they remember the terms, they remember what it looks like, they just don't remember how to do it. So that's a good thing. At least you've seen it once before pre-calc. This rule can be super, super, super tedious. Like long, I would not want to do it for a very big problem. but the reason why you're kind of forced this route, you don't want to set up a table because that takes way longer. You can't do quadratic because maybe it's over a power of 2. Like mine's power of 3, you can't do quadratic yet. And you can't factor it. Like you just don't know how to even start the route, the factor, because maybe it's like a power of 5. You can't even factor that thing with grouping. So you'll have to eventually do the rational roots. Now the other one is just to guess and check and just skip it and go on to the other steps. Okay, but let's factor mine so we get like kind of a sense where this thing's going. Again, the whole goal is just to figure out x-intercepts. Where do I hit the x-axis? It's called zeros or roots for a reason. So let's factor this thing apart. This is a grouping problem. It's 4 terms across. They don't all have something in common, but I can still factor and I can figure out where my x-intercepts are. At least 1 or 2 of them. I think I should be able to at least find 1 if I factor this thing apart. Okay, what do these 2 things have in common? X squared. Take that out of these 2. I'm doing grouping, so I group the first 2 together. So if I take an x squared, that's an x left over, and that's a minus 4 left over there. In the back, grouping that up, bless you. I'm going to take out a 5.
Thank you.
Take out a 5. And so once I factor out the 5, then you can notice that they both have something in common, like this first and that back. So I'm going to take that out.
No.
Like this. Okay, this is the factored version of the top thing. That's the factored version. Now, what we have to do is figure out how do those parentheses equal 0 if they can. So let me stop the camera so we can get the whole thing on film.
Smile.
It stops after like 25 minutes or so. So just like stops recording. It's got a limit, yeah. So I got to remember like the middle of the class or stuff. All right. So now, how do I make this thing equal 0? Is there any possible way I can put a number in there and make 0?
-5.
-5. If I do -5, -5 squared would be 25, and you add 5, that's 30. No, it's not 0.
Wait, do you have to set up a,
You know, Bryce, that was a nice attempt. I appreciate it.
2.2360679.
no, you have to set up a square root, don't you?
Nope.
You have to set up a square root.
No.
No?
You can't make a 0.
You can't do it. It's impossible.
It's impossible.
It's impossible.
Because when you plug in negatives, when you square it, when you square a negative number, it turns positive, you add it to 5, so it'd just be a bigger number than 5. If you plug in 0, the smallest it will be is 5, it'll never hit 0, so there is no intercept on that part. So knowing that it's squaring, I can't make an intercept there. I know a lot of you want to set it equal to 0, subtract the 5 over. You can't square a number and make a negative, just saying.
So is it just going to be plus or minus 4?
Just plus 4. This is the only root that we have. It's the only root. So in this problem, I'm only hitting the x-axis at, what is it, -4, +4? I'm only hitting +4.
Wait, but if it's to the power of 3, doesn't it go through?
Potentially it has 3 roots. I don't have 3. I have 2 that are imaginary.
Wait, what about?
Because it was so, like this thing was shifted so far down, what it's doing is it's probably doing something like this. It's probably doing something like that, where it didn't actually pass through the x-axis 3 times. It only hits once because that one tail is going up far enough. Because, how I know that? It's just because it's a -20, that'll come up with the next rule. It's so far shifted below the x-axis, it probably didn't have enough time to go up and pass through a couple times. Now, if this didn't have a -20, let's say I had a +5, I might have been shallow enough where it might actually hit 3 times and have 3 x-intercepts.
Oh, so like the way the slopes work down.
Yeah,
it's still gonna-
exactly. Yeah, it's the way that the actual slopes work. So, okay, all right. But I have at least 1 x-intercept. Now, the next thing I have to figure out, and this will, again, this one only had 1 x-intercept. If you didn't hear Carew, this thing had potential for 3, because what's the highest degree? 3. So it has potentially to have 3 x-intercepts when you factor it apart. These 2 didn't happen. There's 2 in there. They didn't happen because you can't make this into 0. It's not possible. Okay, so it does only have 1 in this case. Okay, now let's go to the next rule. We're at step 4 now. Step 4, and we'll come back to that. I don't know if yesterday if I had put the step on here, It was called the Multiplicity Test. I don't know if I put it, okay.
Is that where you take it times negatives?
Yes. All right, the Multiplicity Test works with your X-Intercepts. This is where you look at, are you bouncing or passing through? Okay, so here we go. What's the power on this parenthesis right here? 1. Well, we didn't have any X-Intercepts, so I'm not even considering that. I'm throwing that one out. What's the power on this one?
1.
1. And that one just is one X-intercept. This is one root, right? Since the power is of 1, the multiplicity test, since it's an odd power on the parenthesis, means you're actually going to pass through that number. It's an odd number, odd power, so you pass through it. If there was a 2 here, maybe somehow we factor this apart, it ended up being a 2, that means we're going to bounce off that X-intercept. It would go up, hit that number, and then turn around and go the other direction. It won't actually pass through the X-axis. My second example today will have one of those so you can actually see what it looks like. So I'm going to try to put that up today. But this one only had a 1, so the multiplicity test says I actually pass through, and that's actually what you're seeing there. That justifies what my answer is. It's got to pass through 4. Okay, Y-intercept. This is number 5. The Y-intercept. I think this is a rule somebody was hinting at earlier. You have to plug in a bunch of zeros. Okay.
Or just like a last number.
What?
Or just like at the last number.
Yeah, it's the last number. But again, for the Y-intercepts, you plug in zeros to everything, or just the common sense way, it's the last number that's written, as long as you don't have a lot of constants here. So if I plug in a bunch of zeros here for the X, or for the Y-intercept, to all the X's, it turns out to be negative 20. So that means down the road at negative 20 somewhere down here, 0, negative 20, that's a Y-intercept. So somehow something's doing this, and it's probably coming up right through it.
At 1, it's negative 18. At 2, it's negative 18. How does that work?
So at 1, it's at negative 18,
And at 2.
and at 2, it's at negative 18. So
Yeah.
probably what
And at 3, it's at
happened,
negative 14.
so probably what's happening is you said 1 was at negative 18, and 2 is at negative 18. It's probably doing something like this, where it's coming up and it's flattening out and going.
Then it goes to 14.
Yeah, so it's probably doing that. It's going up and that's where it's flattening out. It's not actually doing like 2 curves. It's going up and flattening and then going up again.
That's weird.
Yeah. So again, the table actually helped us figure that out, I bet. So 0, 2, or 0, negative 20, I should say. All right, but this tail is going down that direction. All right, next, the next rule. Is this thing symmetrical across the y-axis? I'm going to say it's not, just because when I'm looking at, this picture doesn't look like it's going to be the same on this side versus this side. Now, if we didn't actually have what Luke said, another clear sign that would tell me that it's not symmetrical, it had 1 x-intercept, it had 4, but it didn't have negative 4 on the other side. It's not balanced across the y-axis. So, it's probably not going to be, just because of this simple fact. Now, the rule that we use for the symmetric rule, so this is rule number 6. We only have one more rule after this. So, the symmetric rule. And this is a rule I don't believe we got to see on Friday. There's 2 types of symmetry. When you're going across the x-axis and you're perfectly balanced like this, where you're balanced on both sides, that's called even symmetric. Where the pictures on this side are perfectly images on this side. And then there's odd symmetry, where they're perfectly balanced like backwards to each other like that. We could have had odd symmetry on this problem. It could have been like that. But what gave it away that it wasn't, is that it had only 1 x-intercept over here and not a second one. It would have had to do a similar situation like this, and it wasn't perfectly balanced. So, okay, so I'm going to show you the rule for how do you know if it's even or odd. I'm going to show you the shortcut. So it takes you 1 second to figure out if it's even or odd or neither. Let me turn that off here. I lost Wi-Fi connection.
We're not 50 years old. Do you watch Cheers? What?
Cam, do you watch Friends?
Yeah.
Ethan, do you watch Friends?
I have before.
Cam, do you watch Friends?
Why?
Alright. So, hey. Alright. So we went through those two numbers, my x-intercept, y-intercept. Now to figure out if this thing is symmetric or not, here's what you do. Here's your test. It's the easiest thing in the world. You take and you plug in a negative x into your function. And you check what is the function going to do. So, here we go. You're going to plug in a negative x into any x that you see on that problem. And you're going to do the simple simplification and see does it turn out to be the exact same as what you started with, or the exact opposite, or neither. And that'll tell you what type of symmetry it is. So on an odd power, so now this is just common sense. On an odd power, what happens to the negative sign?
It
Stays negative. Okay? What about an even power?
changes.
Turns positive, okay? So x squared, so cancel out the negative sign. Odd power, this is a power of 1, we'll keep the negative sign. And then 20 didn't change because there's no x on it. Okay, was this exactly the same thing that we started with?
No.
No. Is it exactly the opposite of what we started with? No. So this is not symmetric. And again, I could have told you that from the graph. This is not symmetric. Stop moving around, guys. Okay, so we don't have any symmetry on this one because of that. I could also tell you from the graph it didn't have symmetry because it wasn't balanced across the y-axis. So there has to be symmetry, but on this one there isn't. So the last test we did the leading coefficients, x-intercepts, y-intercepts, multiplicity test to figure out if it's bouncing or passing through. Figure out the y-intercept, figure out symmetry. The last thing is how many turning points should this thing potentially have? What do I mean by turning? You look at the biggest power and you subtract 1 off of the biggest power. So how many points will this thing turn directions?
2.
Twice. So, if this thing potentially turns twice, this is what I'm talking about. Gentlemen, you guys can go, leave. So, you guys don't want to learn, go sit out in the hall. I don't care. Go, now. Get out of my room. Go, you 4, or you 2, go. Go, poking each other.
Am I included?
Yep, go. Bam, out the door.
He was poking me with the pencil.
Don't care, get out my door.
Very good.
You don't want to learn, get out. You're facing backwards half the time anyway. Go sit out in the hall. You guys can learn it on your own. So, turning points. If this thing's going to turn twice, that's the idea of turning twice. It's going up this direction. It turned once, it turned twice from its original direction. It turned twice after the original passing. That's what this thing could potentially do. It had a 3, but it potentially turned directions twice. That's the concept.
So you don't have to use
Okay.
all 3.
Now, we don't have to use all 3. It's always the number minus 1. So it will potentially use twice from the first. Now it doesn't have to, because like even Brown said, like this thing looked like it leveled out at about -18, and then it went up again.
Does that count as a...
So that would be a turning point, right? It turned directions and then turned again. So it like leveled off and then went up again. So instead of doing like this radical turn like this, what mine could have done is it could have done this, and it just was the smallest change in the world and you just didn't see it. That's the concept. And so that's what we're looking at. All right, so if you have your Chromebook, take it out. I want you to go to Desmos.com, and I want you to type this in, and we're going to take a look at it.
X cubed minus x squared plus 5.
Yeah, type in that original item. Okay, next problem. Okay, if you typed it in, if you type this in, I want to talk about what we have here. Okay, now I don't even have the original polynomial, you guys just type these in. What I want to get through is I want to get through end behavior, the leading coefficients, really quick because I already know my X-intercepts. Okay, so here's the idea. If I were to multiply all of these together, right now as it sits, without even foiling, what would I get for the biggest power? X to the fourth, right? Do you agree with that? And in fact, it would be a 1. These are all 1s. I would actually get a 1, a positive 1 out front. Agreed? So, without even doing all the math, I don't even care about all this other stuff. I know that my biggest power is a 4, so the tails on the outside of this graph are going the same direction, and they're going up. Because what gives this away, the leading coefficient, the biggest power, the number out front was a 1, it's positive, that means the tails are going the normal direction, they usually go up on a power 4. On a power 4, since this is an even power, the tails go the same direction, so they're both going up. So this is what my graph will look like on the very, very outsides. Does that make sense? Okay, now next. I'm done with end behavior, I'm done with leading coefficients, because I already knew if I were to multiply that, that's what it would turn out to be. X-intercepts. I already know my 4 X-intercepts. So you have to double check. Did it actually hit, let me get rid of all these 1s. Did it actually hit -3, +1, but I'll talk about that one here in a second, and -8. Did it at least hit those 3 numbers? Yes. So -8, -3, and +1. Now, here's how it works. Now, I'm done with the X-intercepts because I already had it factored. I just gave you the problem factored apart. Let's do the multiplicity test. What was the power on this X plus 3? 1. That means I'm going to pass through, on the multiplicity test, I have to pass through that number. So at -3, you're probably watching your graph was probably passing through it, correct? Next, what's your multiplicity on this 8 over here? A 1, so it's passing through that. So it's probably doing this. It's turning around and going right through the 3 again, somewhere in that range. Okay? Now, the multiplicity on the middle terms, do you agree that these two parentheses are exactly the same? So that means there's 2 of them. Right? There's 2 x minus 1s. So the multiplicity test says that my power is a 2, it will bounce off of that number. So probably what happened, it did this, and it bounced off and went up. Is that generically what your graph looks like?
Yes.
By doing my simple checks, that's exactly what the graph looks like. Now, here's the problem. I don't know how high it went, like right here, and I don't know how low this part went. But I generically know that it passed through them and it bounced off the 1, and it was a little more flat than what I have drawn there.
It hit
Okay.
a Y-intercept at -298.997.
The Y-intercept at what?
Oh wait, no, sorry, no, that's the lowest point, sorry.
Oh, okay,
That's the
yeah.
lowest point, never mind.
Yeah, so it was way down there.
Yes,
My
sir.
Y-intercept should be like 24.
Yes.
Yeah,
Okay.
sorry.
Now again, how I did all the multiplicity tests is the powers. These 2 parentheses combined make 2 of them because they're the same parentheses. The Y-intercept is you just plug in all these zeros in. So that's 3 times -1 times -1, which is 3, times 8, which is 24. And so this spot right here should be 24. I don't know if that's the highest point, it's somewhere around there. And then it turned around and it bounced. And now that hilltop could be way past 24 for all I know. Is this thing symmetrical? Definitely not. I'm looking at a picture, it is not symmetrical from the left and the right side. They don't look the same. And did it have at least 3 turning points? Because this thing had a biggest power of 4. So if you subtract 1, the turning point test says how many times will it turn directions from where it originally was going from left to right. It turns once, twice, 3 times. That's what your picture should look like. Is that generically what we have?
Yep.
Again, I don't know the highest and lowest points of the graph. Like we even said, it was like -200 something.
Yeah.
That's silly. The reason why, what we would do in like calc to figure that out, we do your differential quotient you did on the last test, and we figure out what makes that thing 0 on a differential test.
-298.
Yeah, it's crazy. And we can do that, but that would take all the rest of your time today. Okay, if you were gone on Friday or some point last week when I handed out that 216, the transformation stuff, make sure that you are getting that done and complete. I want those in as soon as possible because I want to enter those grades in the next quarter here. Okay? Make sure that tomorrow you bring your math book, you bring your Chromebook. We're going to be drawing a bunch of stuff tomorrow. I'm going to have you in, I think this is like the later section of chapter 2. So make sure you are ready to go. Okay, because we're out of chapter 1, we're in chapter 2 stuff. Okay, you know, it's the third unit for us. Okay, so that's it. Calculators. Right now we still cannot use a calculator in here, so get used to it. I'm still missing one of my calculators, so if you know where they're at, or you know where the one is at, try to bring it back.
If your son's a gun,
So for the next week or two, or even longer, until I get my calculator back that should be in that caddy, we will not use calculators in here, we'll do everything by hand, including foiling.
does that have to be that exact calculator? Can we just get
I
you
want
a
my calculator back, so.
Mine.
Can I give you
How
one
will you
that's
know?
the same?
Nope,
How do you
it's
know?
the principal that counts, I want mine back.
What if I get you a graphing hook?
Nope.
How do you know?
My calculator back, it's the principal that counts.
Hey, Mr. Ward, I think I found it.
Well, yes.
Where?
No, not that.
We'll just have NASA donate money.
Are we?
Yeah.
Ward, are you going to open gym?
Yes.
Me too.
That's what I like to do.
Oh,
Let's just get NASA to donate one of their supercomputers. What if we did use?
Actually, I built one.
What am I back?
eventually we were back to these companies.
So basically,
We're in everything by hand.
You got it. You got it now. Let me see.
We won't.
Oh, not yet.
yeah.
Like on the test and homework.
There it is.
I mean, that'll help us.
And I can
So
tell
you
you.
got it. It's not. It's literally. It's like I don't know. It went down on me.
I don't know what number my dad.
Oh yeah, it was this.
I have to teach
Do you want these desks back a certain way?
Nope, I'll put them back later.
Boards?
What? From last week.
What a nice.
We did some stuff in class together, but that was only actual books. Okay.
I don't even.